Okay, so let's start. So we are glad to have Dr. Shobhik Raichaudhuri today. So Shobhik did his bachelor in engineering from Jadavpur University in electrical engineering, and then decided that he likes physics more, and he went on to do his integrated sort of master's and PhD from Harishchandra Research Institute in Allahabad. And then he was a postdoc at IIT Bombay for a couple of years and IUCA for a year, and then he went to the Asia Institute, the Academia Sinica Institute of Astronomy and Astrophysics, where he's a distinguished postdoctoral fellow now. And Shobhik works on the interface of particle physics and cosmology, and is currently working with large cosmological surveys to, among many things, to constrain neutrino masses. And so he will talk about that today. So, Shobhik.
Hello, everyone. Thank you for the nice introduction. So yeah, I'll talk about cosmology in an extended parameter space, and I'll focus on dark energy and neutrino masses. And it will cover the recent data release from, this was last year's data release. So my work is on last year's data release, but I'll also talk some implications of the new data release. So
just click on it once. After that, I think.
Yeah, I think it's working.
Now there.
Yeah, so this talk is based on this paper written with Tepe Okamura, who is a research fellow at Asia, and so this was published in Astrophysical Journal Letters. So I'll start with something very basic, and that is that so we have basically three kinds of components of or constituents of the universe, which is radiation, matter, and dark energy. And radiation in the early universe, the radiation energy density dominates the other constituents of the universe at very early epochs or very high redshifts. So this is close to 10 to the power 4. And at that time, radiation was dominating. But at some point around a redshift of 3,400, we get matter radiation equality, and radiation density basically falls off much faster than matter density, and as the universe expands. So we have then a matter dominated era, and somewhere after radiation, around I think 10 to the power 3, we have the recombination where electron and protons come together and form neutral hydrogen. And so now light doesn't have any charged particles to interact with. So there basically CMB, or the cosmic microwave background, the photons, they decouple from the other baryons. And then there is this CMB is what we see now, and CMB data is something that we'll use in this work. We also have dark energy, and if it is a cosmological constant, then its energy density remains constant over the evolution of the universe, and only at recent times dark energy has become the most dominating constituent of the universe, basically, if we consider the lambda CDM cosmology, which is lambda called dark matter, and lambda is the cosmological constant. But it's not necessary that dark energy density will remain constant. It can vary over time as well. But remember that the effect of the variation will only be effective close to this present day, because not very long ago, because dark energy is very subdominant in the early universe. So only close to the current epoch do we worry about the evolution of the dark energy.
So, Shobhit, the blue triangle, that's your what? Error bar on the energy density or?
Yeah, it's sort of taking I think -1 plus minus 0.2 for the equation of states. So CMB has fluctuations in it. So the main big fluctuation in CMB is actually not 10 to the power -5, it's 10 to the power -3, which is a dipole. And this dipole happens due to our motion in respect to the CMB frame usually, but we typically separate it out, and then you get fluctuations at the level of 10 to the power -5. So CMB temperature is currently 2.725 Kelvin. And you can imagine how small these fluctuations are. And we expect these fluctuations to come from these temperature fluctuations, basically, to come from inflation. The quantum fluctuations in inflation are carried over to the fluctuations in the CMB. And so, as you can see, this is the temperature correlation plot or temperature power spectra. And it has oscillations. And these oscillations are there because CMB and baryons in the early universe are coupled together as a sort of as a fluid. And there is a repulsive force, which is the radiation pressure, and there is the gravitational pull inside. So these two opposing forces create this kind of oscillations that you see in the temperature power spectra. And there is also polarization generated close to recombination. So when there is equilibrium at very high temperatures, then there is no polarization generated. But when it is close to recombination, when everything is going out of equilibrium, then we get a polarization map as well from CMB. And you can see that we can cross-correlate with temperature, which is the TE power spectra, and also the E mode polarization power spectra. So the mode we get, we name it E mode, and there is another mode at 90 degrees, which we call the B mode, basically, which is perpendicular to the E mode. So apart from CMB data, we'll also deal with baryon acoustic oscillations. And so, as I said, there was these photons and baryons are coupled together, and then in recombination, the baryons, the photons decouple from the baryons. And so the actual decoupling happens slightly after recombination at the drag scale, which is the co-moving drag scale is written as RD. So the baryons sort of get frozen, and you get a bit of over density at this. So there are pressure waves in the CMB and baryon fluid, and these travel to a particular distance. And at that distance, you can see over densities of baryons. And when you look at galaxy surveys, then you can infer these over densities at a particular distance, basically. So that distance is RD. And what galaxy surveys actually measure is these two kind of things. One is transverse to the line of sight, another in the direction of line of sight. So these two things BO surveys can measure. And it is, this is slightly blocked, but basically BO essentially constrains two cosmological parameters, which is omega m and this H naught multiplied by RD. So from cosmology point of view, baryon acoustic oscillations is technically a background probe, not a probe of perturbations as CMB. There is also uncalibrated type 1a supernovae. So type 1a supernovae are basically thought to be from binary systems of white dwarfs, where one white dwarf gets enough mass from the other star to get to the Chandrasekhar limit, and then it basically blows. And it doesn't leave any remnant. Like core collapse supernova, you get a neutron star or black hole, but type 1a supernovae usually don't leave any remnant. The thing about this is, however, is that since this explosion happens at a particular mass, so you get a peak brightness which you can standardize. So these are called standardizable candles. So when you standardize the light curve, you get a particular magnitude, a peak magnitude, and then it falls off basically. So this is the B band light curve. And again, these are this type 1a supernovae are sort of background probes, and it basically measures this quantity H naught DL, where DL is the luminosity distance. So in both cases, uncalibrated type 1a supernovae or BAO, you do not measure H naught directly. Only so you might have heard that in local universe supernovae measure the H naught, and that happens because the luminosity distance is usually calibrated using other stars like Cepheids, which are a type of variable stars. But uncalibrated type 1a supernovae are actually sensitive to the integrated cosmological evolution close to our universe, close to our present day, basically. So this data also, the luminosity distance measurements also constrain omega m very well. So these BAO and supernovae, both of them are independent measurements of the matter density, omega m. So now we go to the DAISY BAO DR1 result, which was published on arXiv last year in April, and so around 1 year ago. And so we take the dark energy equation of state to be a something that varies with redshift, so it varies with time, and it has two parameters, W0 and WA. So this is a particular popular parameterization of dark energy, dynamical dark energy, which is called the CPL parameterization. And this is useful close to our universe because in the early universe, Z is large. So this is basically constant to W0 plus WA, more or less. But if you see Z, which is close to 1, so our universe at present is at Z equal to 0. So, but if you see close to Z equal to 1, then or later, then you see that this variation matters. So, and we are, as I said, we are interested in dark energy evolution close to our present day because dark energy domination starts at late times. So, what they use is DAISY BAO plus CMB data, which has plant data plus lensing, CMB lensing as well. And it also has three kinds of supernovae data, uncalibrated supernovae data, Pantheon plus, Union 3, and the Dark Energy Survey Year 5 supernovae. And what they find is that this point, or the cosmological constant, which is W0 equal to -1 and WA equal to 0, this is disallowed at the level of 2.5 to 3.9 sigma, depending on the data set used. So Pantheon plus gives 2.5 sigma, Union 3 gives 3.5 sigma, and DSY5 gives 3.9 sigma. And this has changed in the DR2 results, which came out recently. So that evidence has increased by a 0.3, so 2.8 to 4.2 sigma, basically. Another problem that was found in the DAISY BO results is the result on neutrino masses, and the constraint that they get in the lambda CDM plus sum of neutrino masses model. So there is no varying dark energy here. The bound is 0.072 EB, which is quite strong, and they only use CMB plus DAISY data, not supernovae, because lambda CDM is actually disfavored when you consider supernovae data together. Now, but the bounds relax to less than around 0.2 EV if you have a dynamical dark energy model. But again, so why it is problematic? Because we do not have any detection. I don't think this is working. So we basically do not have any detection. We have an upper bound, and if you extend this this posterior distribution to negative values, then you see that it will actually peak in the negative value. So cosmological data sort of suggests that the neutrino mass should be negative. So people have written papers on this, and this is one particular concern regarding the current situation in the lambda CDM model.
So, Shobhit, sorry, I don't know why the black thing is coming here, but as you said that it's pretty relaxed when we use the dynamical dark energy, the daisy beta, because now it's like less than 0.2 eV compared to the bound which is 0.072 eV, right?
Yes.
So, what was the reason that the bound got relaxed by such amount? I mean, it's just because more
parametric degeneracies with W0, WA. So, yeah, but the thing is, most people still are in favor of lambda CDM model, even though the data does not show that. So people were very skeptic regarding this bound. So they are skeptic regarding dynamical dark energy. And hence, this got a lot of attention because now the bound is such that if you basically if you extrapolate this, the posterior will actually peak at negative neutrino masses. Sorry.
But
So
that is just a mathematical extrapolation.
Yes, not physical. Yeah.
Not physical. So why should I consider that as such?
Because we are supposed to get a constraint. We are supposed to get a detection of neutrino masses, but we are not getting that.
No, why should I consider the probability for a negative mass?
Okay, it might not be negative mass, but it might suggest that there is neutrino decay, so that you are not seeing the neutrino masses, the effect of neutrino masses. So something like that. There can be other theories also which mask the effect of neutrino masses, then you won't see that effect. So that kind of physics can be there. So now minimum mass required in normal hierarchy. So neutrinos have 3 masses, and minimum mass happens when the lowest mass is 0. So there are 2 hierarchies. In one case, M1 and M2 are at the bottom and M3 is at the top. And in the other hierarchy, which is the inverted hierarchy, where M1 and M2 are larger than M3. So M3 is the smallest mass. And this sign of this bigger mass square splitting is not known basically. So that is why you get 2 hierarchies, possible hierarchies.
But it's not that there has to be that mass difference.
Yes, otherwise there won't be any neutrino oscillations.
Not only that, you know that from beta decay experiment.
Yeah.
You know that mass difference quite well.
Yeah.
But not just mass difference, it's also the fact that 2 of them are same and the other, or at least 2. Is it 2 to 1? It's almost degenerate. So that's from atmospheric.
No, that is from solar. 1, 2 is from solar actually.
Yeah.
The 1, 2 square solar, which is almost degenerate, and then 2, 3 square is for.
Yeah, but it can't be 0 because if it's 0, then there is no oscillation. So the minimum mass required for normal hierarchy is around 0.06 eV, and for inverted hierarchy it is 0.096 eV or 0.1 eV.
But how this is
So-
square root of that or what?
Yeah, you just take the mean values and use square roots and all that. So
The lower cut, the lower mass.
the lower mass bound.
It's still like that.
So now the thing is that this mass bound of 0.072 eV is sort of ruling out the inverted hierarchy, even though we don't have any detection of the neutrino masses. So that is one concern here, because we don't have a detection, but we are still saying that we are ruling out inverted hierarchy at more than 2 sigma. And this bound of 0.072 eV, this has changed to 0.063 eV now with the BO DR2 measurements of DESI. Now, what is the problem in lambda CDM? So the problem is with omega m basically. So Jay-Z Bao collaboration. So this is the new paper which came out this year. It should have been 2505.
Yeah, just like,
Sorry.
no, I think.
I think this one is wrong. Yeah, this archive number is wrong basically. So this one is from the new paper, and you see that omega m of CMB does not quite match with Daisy. So omega m of CMB is slightly larger. Omega m of Pantheon plus and other supernovae are also even larger than CMB, and omega m from Daisy BAO is actually lower than CMB. So they have overlaps with them, but now CMB, what it measures is this quantity omega C plus omega B, small omega C plus small omega B. So there is a H square multiplied. This parameter is very well measured by CMB. And now there are independent constraints of omega m from BAO and supernovae. Now, if you consider only BAO and CMB, then what? To get detection of neutrino masses, we need small omega m to be greater than omega C plus omega B. Thus, if you use BAO data, then what is coming out is that omega m becomes less than omega C plus omega B. And then you don't have any detection of neutrino masses. But if you just use CMB data with supernovae without using BAO data, then you can get a detection. So that is interesting because here omega m is larger than the CMB omega m. So you can allow for neutrino masses there.
But even earlier,
Yeah.
your omega m was lower. Means WMAP and other results. At that time, omega m was lower compared to whatever omega m Planck is saying, like higher than 0.3 or so.
Okay.
At that time also,
We had
that neutrino masses.
Yeah.
So,
But that depends
But,
on, I don't know what was the issue with omega B.
I think
omega B
No, no.
omega B had not changed too much.
omega B plus omega C is well
Omega-
constrained by the data. But the thing is, WMAP had only up to L equal to 1000. And the issue is also that it had larger error bar. So I think omega m, the constraints on omega m might have been much wider
No,
at that
no,
time.
No, I-
Much better.
it's not so wider, it's close to that, and you are right that the best fit was probably, here the best fit is what, 0.32 is something, the best fit? From
0.3,
young,
0.32. Yeah, yes.
So that was what, 0.29 or
0.29 or
wait,
0.28 kind
we
of.
have to see what
Okay.
is the error bar.
But then did you have any BAO data or
No,
something?
no, they didn't have
Oh,
BAO over that.
Okay, then the issue is that that is in lambda CDM. So what CMB actually measures very well is the small omega m.
Correct?
Correct.
Small omega m is capital omega m multiplied by h square.
Correct.
So there is a strong degeneracy between omega m and h square when you vary neutrino masses. Neutrino masses will add a component of omega nu. And if you have neutrino masses varying, then what happens is that omega m is not same as the lambda CDM omega m. It can increase, and then basically you get a strong degeneracy between H naught and omega m and H naught and some of neutrino masses as well because of that. Because the main constraint is on small omega m, not on capital omega m from CMB. You get a strong constraint on capital omega m only because you are assuming lambda CDM. But BAO and supernovae, they are sensitive to capital omega m, not small omega m. So if you don't have BAO data, the degeneracy breaking doesn't happen. So you don't get a good constraint on some of neutrino masses without BAO or supernovae included.
In lambda CDM, the neutrino mass is considered to be not varying.
Yeah, it's 0.06. It's fixed to 0.06, the minimum mass.
What is the justification for that? Why?
The minimum neutrino mass,
why-
minimum required.
Mass would be the minimum neutrino mass when it's lambda CDM.
Yeah, because you are not varying some of neutrino masses, so you have to fix it at something.
No, but you use that as also the
Yeah,
parameter.
I think you have the.
No, you don't.
posterior of- See the distribution. of
You
the-
don't have neutrino masses posterior when you have only lambda CDM. When you have sum of neutrino masses, then we don't write the model like that. We write it as lambda CDM plus.
It's very,
No.
Even if it's.
We write it as
No,
lambda CDM plus sum of neutrino masses.
Sum of
No,
neutrino
let's
masses.
see, but let's say even if I fix it, what is the justification? Why should it be fixed? What is the justification for?
Because lambda CDM is a 6-parameter model, so.
Or
sum of
you don't
neutrino
want
masses-
to vary the.
No,
Yeah,
that's what
you
you
don't
don't
want-
vary. You don't vary there. But even if there you can vary it.
Yeah, that is what we are doing. And then,
No. Even in tank paper, they
You
do
can.
vary.
yeah, even I do.
So that is even lambda CDM. So
That is lambda CDM plus sum of neutrino masses, one extra parameter.
So he's saying that in the most
That is lambda.
most core basic lambda CDM neutrino mass is assumed to be
no, but
constant.
lambda
But you
CDM
can change it.
omega n, omega n.
It's a 6-parameter lambda CDM. I think you should.
How many parameters we
Yeah.
are fitting? Go ahead.
Yeah, please move on. We understand.
This is 7-parameter model. Lambda CDM is strictly 6-parameter model. That is why omega m, capital omega m and small omega m both are constrained very well. But if you go to lambda CDM and vary also sum of neutrino masses, then this is well constrained, but this is not because omega nu varies. So there is a direct degeneracy between capital omega m and H naught, and also a straight correlation on H naught and sum of neutrino masses. And that is why sum of neutrino masses can't be well constrained in that model, in this model, when you have only CMB data. Now you need BAO to break this degeneracy or supernovae or together. So what I'm saying is that since BAO omega m is smaller, this creates this issue that small omega m becomes less than omega c plus omega b, and hence we don't see a detection of neutrino masses because we need omega m to be small omega m to be greater than omega c plus omega b. There is this tension as well. You can see in the omega m H naught RD plan. So these are the two parameters well measured by DAISY data, and there is a correlation direction there as well. So DAISY DR1 had larger contours, and DR2 has increased the number of galaxies, almost doubled it, and so now it has even smaller contour, and it doesn't match with CMB that well. So as you can see that DR1 and DR2 are quite okay with each other because it just shrinks the contours, but the issue is it doesn't match with CMB that well anymore. So now CMB plus BAO without supernovae data also suggests a dynamical dark energy with the lazy DR2 results. So this tension in this omega m is partially driving this detection of dynamical dark energy, especially with DAISY DR2, because in DAISY DR1, CMB plus DAISY did not exclude cosmological constant at more than 2 sigma, but now it does. So neutrino masses also have an effect on the power spectrum. So matter power spectrum, and what happens is that after neutrinos become non-relativistic at late times, because neutrinos have mass, so they have a peculiar setting that in the early universe they behave as radiation, but in the late universe they behave as matter. But still they have higher thermal velocities and they do not easily cluster in the galaxy clusters basically. So they suppress the matter power spectrum at small scales, which we can see here in these two plots. And that effect is also affecting the CMB lensing. So CMB gets gravitationally lensed by the power spectrum. And if you have a suppression of the power spectrum, it basically means that if you have neutrino masses, then there will be less lensing. So now in Planck 2018 or Planck PR3 likelihoods, there was something called a lensing anomaly. So it is the black curve where this A lens parameter or AL parameter was more than 2 sigma away from A lens equal to 1, which should be the predicted value. So what is done is that the lensing due to the power spectrum is separated from the power
By
spectrum
lensing
itself.
By lensing due to the power spectrum, it is lensing due to the intervening matter.
Yeah.
Right?
Yeah, lensing due to the
Intervening
large scale
matter,
structure.
large scale structure.
Yeah. So what is done here is that in this Allen's parameter is that the lensing due to the lensing potential is sort of artificially separated from the power spectrum because these two are related. And now the scaling of this lensing potential is done with this AL parameter. And what is seen in the Planck PRT power spectrum, not the lensing measurement, the power spectrum measurement, because lensing measurement is from 4-point correlation functions, whereas the power spectrum measurement is from 2-point correlation. So in Planck PR3 likelihoods or the Planck 2018 likelihoods, there was a lensing anomaly where A lens was 2 sigma away from its predicted value of 1. So theoretical prediction was should be A lens equal to 1 always. But this parameter, which is not a physical parameter, showed that there is more lensing preferred by the data than there should be. But in Planck PR4, in the lambda CDM model, they showed that so in Planck PR4 means the Planck PR4 likelihoods, they reanalyzed the data. There was an increased fraction of the sky as well in the data. And they showed in the lambda CDM model that the lensing anomaly is resolved, especially with the Filipov PR4 likelihoods, which is there are two types of likelihoods, ChemSpec and Filipov. So the Filipov likelihoods show that in lambda CDM at least it's decreased to less than 1 sigma. But nobody has done it for dynamical dark energy. There is also the Hubble tension, as you might know, which has so there is a 5 sigma tension between the H naught measured by Planck and the H naught measured by the Schulz measurement, which is using the local supernovae and using Cepheid to calibrate the distances. So the orange contours are from the measurement using the local universe, and the small blue contours that you see are from Planck. And BAO data basically does not constrain, as I said, BAO data constrains multiplication of these two quantities. So you get a parabolic type curve in there from BAO data. So BAO is in agreement with both of them, but to solve the Hubble tension, you need to actually reduce this RS drag or RD by around 7%, because Planck prefers a value of 147, whereas the local measurement prefers a value of around 138. So how to solve that? We can use NF as a solution that if you increase if you have extra radiation species like neutrinos, then it can basically solve the Hubble tension if you can at least allow for 1 extra radiation species. So NF equal to 4, because normally NF is close to 3. But the issue is this extra radiation species causes suppression in the CMB temperature power spectrum. So as you increase NF from 0 to 7, you can see that the power spectrum is suppressed, and the same can be seen in the polarization power spectrum as well, that the power spectrum gets suppressed. And so by this way, we can actually give constraints on NF from CMB data itself. And what we see is that NF equal to 4 solution, that 1 extra radiation species is actually more than 5 sigma away. So to solve Hubble tension, simply increasing NF would not be enough, because CMB data puts strong constraints on this parameter. But again, we would like to see how much you can reduce the Hubble tension with a simple extended cosmological model, where we have the 6 lambda CDM parameters and then W0, WA, which are the 2 dynamical dark energy parameters, and then we have simple extensions, which is NF. We want to see how much we can reduce the tension just by reduce the Hubble tension just by adding NF as a varying parameter. We have sum of neutron masses because we want to put some proper bounds on sum of neutron masses where we take care of the degeneracies in with W0, WA, and also the lens parameter, because lensing is correlated with sum of neutron masses. As I said, if you have higher sum of neutron masses, then you would have lower lensing of CMB photons. So these two parameters are also correlated. So, and there is also the alpha S parameter, which is running of the scalar spectral index. So our primordial power spectrum, scalar power spectrum looks like this, where AS is the amplitude and NS is the spectral tilt. And you also have this alpha S, which is running of the scalar spectral index. And we use this because some inflationary theories normally predict a very small alpha S, which is of the at the level of 10 to the power minus 3. So we want to check if there is any discrepancy between data and the expected value. So our main goals are to check the preference of dynamical dark energy. If the preference of dynamical dark energy survives in a largely extended parameter space, we want to provide a robust bound on sum of neutron masses. We want to give a definitive answer regarding the lensing anomaly in a dynamical dark energy scenario with the new Planck likelihoods. And we also want to assess the level of Hubble tension in this 12 parameter model. So we use CMB public release 4 likelihoods along with latest CMB lensing likelihoods and BAO data from DAISY DR1. So our paper is slightly old. It was published in September. So we use DAISY DR1, not the DR2, and we use Pantone Plus and DES-Y5 supernovae separately. So Pantone Plus and DES-Y5 cannot be used together because they have some supernovae which are common to each other. So if we use both of them together, then there will be double counting. So we have to use them separately. It is in Union C, you can use it, but since it's in the middle, we didn't use. Huh? It's in the middle of the two. It gives results which are in the middle of the two extreme zones. So
Pantone and DS here.
yeah. So we didn't use it. So our main results are regarding evidence of dynamical dark energy. So you should concentrate on the red and the blue contours, basically, which are when we use all the data sets. So the blue contours are using DES-Y5 and the red contours are using Pantone Plus, but we have Planck PR4 and then CMB lensing and then DAISY as well. And what we found at the time is that if you increase the parameter space to 12, then the degeneracies between parameters are enough to include the cosmological constant within 2 sigma with Pantone Plus, but not with DES-Y5. But since at least one of the supernovae likelihoods actually allows the cosmological constant within 2 sigma, then you cannot say that the evidence for cosmological constant is robust. And also we find this, so this region here, it is this region above is the region for quintessence or the scalar field model or of dark energy basically. And some amount of parameter space is also allowed with Pantone Plus. So quintessence is also not completely ruled out basically. So we sort of countered the result of DAISY collaboration where they said that there are tantalizing hints for dynamical evidence for dynamical dark energy.
So, but you are saying that with this extended parameter space,
Yeah.
you could still accommodate lambda sigma.
Yeah. Not exactly lambda cerium, but a cosmological constant. So
Yeah, okay.
lambda cerium plus all these parameters basically.
Yes, that's
but
right.
yeah.
Like the lambda. Let's say
Yeah,
the
there are other,
W equal to
yeah.
-1, W is 0.
So for neutrino masses, we had some very inspiring results because so previously you saw that the posterior was peaking at sum of neutrino masses equal to 0, which meant if you allowed for the posterior to go to neutrino masses, negative neutrino masses, it would have peaked at some value less than 0. But here we actually show evidence that the posteriors actually peak at positive masses, even though the mass bound is much weaker because we have a lot of parameter degeneracies, because we have W0, WA, then we have A lengths as well. So we see that there is the bounds are much weaker, but the main point to take away here is that we do get the peaks in the positive mass region, and we also have around 1 sigma detection for CMB plus DAISY and CMB plus DES Y5. So that is one very positive thing that in the future we might be able to detect positive neutrino masses. And the other thing is that we have this bound of around 0.3 eV, which we suggest that people who do model building with neutrinos, they can use this mass bound instead of the very strong mass bound provided by lambda CDM, because lambda CDM is no longer the favored model by the data. So it doesn't make sense to be so restrictive about your cosmological model. And that is why we provided this bound, which can be used by phenomenologists. So in terms of lensing anomaly, we see that with plant PR full likelihood, A lens equal to 1 is allowed within 2 sigma, but not within 1 sigma. So there is a slight shift, but it's still allowed within 2 sigma. So there is no lensing anomaly with plant PR full likelihoods in the extended cosmology. So they had seen for lambda CDM, but we saw it for extended cosmology as well. In regards to Hubble tension, you might notice that with Planck alone or with lensing, there is basically no proper constraint on H naught because of this strong difference between W0, WA and H naught. So what happens is that until you give DAISY and then supernovae data, this W0, WA parameters are not well constrained. And hence there is no proper constraint on H naught as well. But after we add all the data, we find a persistent 3.2 to 3.9 sigma tension with the measurement by Schu's collaboration, which gives you the value of around 73 for H naught. We get something like 68 plus minus 0.1. So there is still 3.2 to 3.9 sigma tension. 3.2 for Penton plus, I think, yeah, 3.9 for DES Y5 supernovae. So Hubble tension is robust. Now S8 tension, some of you might have heard of S8 tension as well. So this is a measurement of the sigma 8 parameter along with omega, so multiplied by omega and divided by 0.3 to the power 0.5. So this S8 parameter basically. And so what we find is that with Planck PR for likelihoods, this tension is reduced to 1.4 sigma, whereas with Planck PR3, this tension was at the level of 2.4 sigma with DES Y3 weak lensing data. So Planck PR for likelihoods actually prefer a lower value of S8 around 0.8 instead of 0.83, which was the case with Planck PR3. So mind you, we are considering all the data combination together, CMB plus BO plus supernovae. So this means that we are getting the strongest constraints possible, and still we find that the S8 tension is actually reduced to 1.4 sigma, and possibly we'll see that the tension will be gone in a few years or even less than that.
Talk about the S8 tension. This is tension between what? Just Planck and then Planck while adding the BO and the S8 values.
It is with Planck and lambda CDM gives very tight constraints to S8.
Yes.
And weak cleansing, also considering lambda cerium,
This is
will give you
just weak cleansing or weak cleansing of the CMB?
weak cleansing, not weak cleansing of CMB, it's weak
Weak
cleansing
cleansing measurements.
measurements using.
Only like DES.
Yeah, something like DS.
So the tension here is with DS year 3 results. And that is reduced to 1.4 sigma. So in future, we might see the SI tension to go away just by itself, more or less.
So, just tell me, these are with your WA non-zero.
Correct.
What
Except
happens to, what was the value for tension with WA is equal to 0?
so if you have only PR4 likelihoods and
Anyhow.
lambda CDM, any just lambda CDM, then this was 1.5.
And that has reduced to 1.4 sigma.
Yeah.
With
Yeah, just
Very
slightly reduced. So basically, it's the plant PR4 likelihoods which are doing, which are giving most of the effect, I think.
Not
So-
just if you assume lambda CDM or you use dynamical dark energy, that's less to do with the, you are saying that it's the Planck PR4 that has already reduced the tension.
Yes.
That has reduced the tension even just by using lambda, W equal to -1 and W is 0.
Yeah.
So if you add to that, that doesn't add much.
Yeah. So there are also other papers which are suggesting now that the tension is probably going away in the future, very close future.
Even deep cleansing, is like part of systematics.
Yeah. For NF and alpha S, we do not find any deviation from the expected values. NF is 3.044, which is the standard model value, and we get everything. We get the posterior which matches with that, and for alpha S, we are supposed to get something close to 10 to the power -3, and that is also consistent. So we don't have a very strong constraint on alpha S right now, so it's difficult to say. But it's consistent with the expected value. So these are some degeneracies. To explain why you get much weaker constraint on sum of neutrino masses. So one is more, of course, the ALMs. Then also some small. So you can see the degeneracy direction from the tilt. So if it is vertical or horizontal, that means there is no correlation. Or if it is circle, the contour plots, if they're circle, that also means there is no correlation. But the tilt of the correlation plots means there is a strong correlation between ALMs and sum of neutrino masses. There is a very small correlation between NF and sum of neutrino masses, and there is again a strong correlation between WA and sum of neutrino masses. And so also when you take care of the W0, WA parameters, then you see that there is a strong correlation between H0 and NF. As I said previously, that if you increase NF to 4, then you can increase H0 to 73 and solve the Hubble tension. But as you can see that the data doesn't prefer NF more than 3.5. So H0 can't go above 70 basically. So that means that the Hubble tension survives at more than 3 sigma.
So you have about 5 minutes.
Yeah, I'm on the last slide. So our main conclusions from this paper was that with CMB plus BO plus Pantheon plus, we still find cosmological constant allowed at 2 sigma, within 2 sigma. So the evidence for dynamical dark energy component is not yet robust. The peaks in the sum of neutrino masses posterior in the positive mass region suggests that in future we might be able to get detection of some of non-zero neutrino masses at more than 2 sigma level. So we can get maybe an actual bound from cosmology, a two-sided bound from cosmology alone. So we also found a bound of 0.3 eV at 2 sigma, which we suggest that people use for cosmology and particle physics model building. And We also find that there is no significant dancing anomaly when we consider dynamical dark energy scenarios. And simple extensions to lambda CDM model that we have used in this paper are not sufficient enough to solve the Hubble tension below 2 sigma level. So the Hubble tension is robust, and the SI tension is less than 2 sigma now, which is at the level of 1.4 sigma. So we are expecting that the SI tension will go away in the future. Yeah, no slides. Thank you.
Okay, questions? Okay, Sian.
I think I already have questions. If there are others,
Others will think of questions while you ask.
Comment your first, then we get.
You have introduced, you have made a few more parameters flexible in the considering the lambda CDM part. You have made a few more parameters flexible, which increases the parameter space, obviously. But then, how do you compare them with the data? So, do you use some reduced chi-square methods, or what is the statistic that you are looking at? To if I want to compare two models, basically.
We use simple Markov chain Monte Carlo method, so you can use chi-square in the sense, so in terms of log likelihood. So
No, I think what you are saying is that in one case you have 6 parameters, in other case you have 12 parameters involved. So then you are saying, how do you do comparison of a data fitting between a 6 parameter and a 12 parameter model? So maybe something like people generally do, like information criteria or something. That's not probably
Yeah.
the question.
you can use something like a KK information criteria, things like that,
No,
using the maximum log likelihood and the number of parameters.
did you do that with
No, we didn't do that. One reason not to do that because we do expect a lot of improvement in chi-square because we are even though it is allowed at 2 sigma, what is happening is that the best fit region would be somewhere here. So basically, we expect that it will improve from lambda CDM quite a bit. So we didn't do the analysis, but we do expect that the chi-square will improve quite a bit from lambda CDM. So even though cosmological constant is allowed within 2 sigma, the best fit you can see would be somewhere here.
Other question?
So I have 2 questions. You can go one. Okay, so about this neutrino mass bound. So if we look at the matter power spectrum, as you showed that the
No,
matter power
yeah.
spectrum will have the effect of the mass of the neutrino.
But we do not have any matter power spectrum
That's
data
right. So
here.
my question is that, is there any current constraints on the matter power spectrum? Or
Yes,
spectrum? Yeah.
yes, there are constraints and it improves a bit, but not much. Currently, the full shape data from DAISY, they have a paper on it, which came out in last November. So it improves the bound slightly, but not by much. Yeah.
And then regarding, I think some of the bounds that you showed here, maybe in this extended, but I don't know, 0.3. So, but that takes care of all your lower bounds for inverted or normal.
Yes,
normal.
yes, yes.
That is 0.0, one order higher.
One
Yeah.
order high. I have another question, but I can go later.
So, instead of 6 parameter, you are now putting 12 parameters. But instead of doing that, if I use WA equals to 0 and do 11 parameter fit, how much is going to be different?
So this you can probably see from here that sorry. So WA equal to 0 would mean this line, right?
Correct.
So you will get something like this small WA equal to 0, right? So
But you're fixing that.
yeah, I'm
I am
fixing that. So
but I'm taking the 11 parameter to vary.
yeah, you'll get some WA parameter close to this. So people have already done this, and In the DAISY paper, when they fix W equal to 0 and only value W0, then they get values which are okay with lambda CDM.
But
So the dynamical dark energy evidence comes out only when you vary
I
W0,
got the
W0.
W dot and W.
Then why should I go for that if I am already getting a smaller quantity with W A equals to 0?
No, because the chi-square would be worse when you fix WA equal to 0.
That was his question. Then how do you compare it? You cannot compare simply chi-square. You have to do something else. Chi-square per degrees of
You can do Bayesian evidence, which is much more difficult to do with 12 parameters, but that is what you can do. No, will not allow it to move